Now let us discuss their physical state. Now in physical state, what you need to know is they all exist as diatomic molecular species, like fluorine as F2, Cl as Cl2, Br as Br2, I as I2, At as At2. And what you need to know is fluorine is a gas, chlorine is a gas, bromine is a liquid. It's the only non-metal which is existing in the liquid state. Iodine is a solid, astatine is a solid. So what we find is that their boiling point increases down the group. The reason is because boiling point is directly proportional to surface area, surface forces. Larger is the area, larger the stronger the forces, higher is the boiling point or melting point. That's why what we find is it's like this. That's why what we find is at room temperature, these are gases, this is a liquid, this is a solid. So that's the basic, we have criteria for this. Then what we need to understand is their bond enthalpies. The bond enthalpies of these diatomic molecular species follows the trend. It's chlorine, then bromine, then fluorine, and then iodine. We believe that fluorine is very small in size, so its bond enthalpy should be maximum. It's not like, it comes in the third place. The reason is that the three lone pairs which the fluorine, small size fluorines are having a lot of inter-electronic repulsions, due to which this bond becomes very, very weak. As a result, what we find is chlorine dominates, bromine dominates, fluorine comes in the third number. Why they dominate? Because their sizes are bigger, so the repulsions are less. That's why. So this is bond enthalpy you have and the physical state. Let us discuss chemical properties of group 17 elements. The first in the list is their oxidation states. Now these elements like fluorine, chlorine, bromine and iodine, they all show -1 as their most common oxidation state, because they all are only one electron short of the noble gas configuration. So their -1 is their most stable, one of the most common oxidation states. When we are talking about other oxidation state, what we need to understand is that fluorine doesn't show any other oxidation state, because there is no other species available which can take out electron from fluorine, so strong oxidizing. Whereas chlorine, bromine and iodine, yes, they show +1, +3, +5 and +7 oxidation states, because the other stronger oxidizing agents can take out their electron from either 1, 3 or 5 or 7 from these elements. But we have to understand this, that only very small size elements with a very stronger oxidizing powers can take out electrons from chlorine, bromine and iodine. So they show these oxidation states either in the form of their oxides or oxyacids, or in the form of their fluorides. Now they form fluorides in their interhalogen compounds, and since all these species are very strong oxidizing agents, they are the only one capable of taking out 1, 3 or 5 or 7 electrons from these three elements. And we know other thing which differentiates them is, since fluorine is not having d orbitals, so it cannot extend its octet, so it's only left out with the 4 pairs, whereas chlorine, bromine are having their d orbitals along with them in the same shell. So they can unpair those paired electrons and can share more than 4 pairs, like 5 pairs, 6 pairs and 7 pairs of electrons. Like we know iodine forms IF7 gaseous molecular species. So these are their oxidation states. Now let us discuss their oxidizing power. Now when we are talking about their oxidizing power, we know that they all are very strong oxidizing agents. The reason being their electronegativities are very high and their electron affinities are very high. Their oxidizing power is like this: fluorine is the strongest, followed by chlorine, bromine and iodine. This can be shown by the following examples. They can show this oxidizing power in solid or in the liquid state like this. Like if we take fluorine and we have any of this X minus, fluorine, this X minus can be your chloride or bromide or iodide, because since it is more powerful for the fluorine, This can take out electron from these X minus, these which can be any one of these, and forms S minus and oxidizes them to their X2 state. So it's like this. What we need to understand now is that since it's the strongest one, it can oxidize chlorine, bromine, and iodine. Whereas similarly, what we can find is chlorine can oxidize X minus, where this X minus is only your bromide or iodide, to like this, chloride plus X2. Whereas bromine can oxidize only iodide like this to what? Iodine and bromide. So this shows their oxidizing power, how strong their oxidizing power is, which can also be proved by their E0 reduction values, which is very clear from the electrochemical series which is there. They can also act as oxidizing, their oxidizing power can also be explained by the reaction in the aqueous medium, like when fluorine is reacted with water, what it forms is basically, okay, it forms F minus, it forms H plus and releases oxygen gas, because it can even take out electron from oxygen, which gets oxidized from -2 to 0 state. Whereas the chlorine and bromine, like here X will be your chlorine or it can be bromine, they in their aqueous medium shows disproportionate reaction to form HX and HOX. Like chlorine forms HCl and HOCl, hypochlorous acid and hydrochloric acid. So from 0 they get changed to -1 and +1, so that's the disproportionate reaction. So their oxidizing power is less. Whereas if we are taking iodine, what you need to know is, that's most important, that what can happen is that this iodine is not able to react with water. Rather what we find is the iodide ion, when taken with H plus ions, with oxygen is the one which can oxidize it, and it gets oxidized to iodine and we get water. So that's why we can see that even in the aqueous solution their oxidizing power changes like this. So that's what the major thing is. Now let us discuss the anomalous behavior of fluorine. Anomalous behavior of fluorine. It shows very different behavior. Like it's the most electronegative species we have. Its bond enthalpies are very high, but of course it's very less than chlorine and bromine. The reason being it's having strong electronic repulsions. It shows -1 oxidation state. That's the only oxidation state it can show. It can oxidize any other species, and it can react with all elements, all elements which are existing in the periodic table. So like this, they are having a very anomalous behavior, and the mainly reason is they're very small atomic size, very high ionization enthalpy, highest electronegativity, and high electron affinity. So all these makes it very anomalous, very different from the rest of the halogens. Now let us discuss their hydrides. All group 17 elements combine with hydrogen to form hydrogen acids or hydrogen halides with the general formula HX. It's like HF, HCl, HBr and HI. Now what we need to first understand is their stability. Remember, it decreases down the group with the increase in the size of the halogen, because HX bond strength decreases. Now what is next to notice is their acidic nature. Since they all will release H plus ions, what we need to know is their acidic nature. It increases down the group because HX bond strength decreases. That's why Hi is the strongest acid, halogen acids, followed by HBr, HCl and HF. So it's like this. Then the third is their boiling point. Boiling point of halogens, always of any other species, depends on their molecular mass or intermolecular forces. So it increases down the group because molecular mass increases. That's why what we find is HCl, HBr and HI are, this is the order in the increasing order, and but the HF comes first. It's not the here at the lowest position. The reason is it has hydrogen bonding, the strongest hydrogen bonding, which makes it what? Liquid, and that is why it is the only halogen acid which is there as a liquid. Otherwise all four other are gaseous in nature. So that's why this is how we study the halogen acids or hydrides of the group 17 elements. Now let us discuss their oxides.